I'll be presenting a measurement study of mobile broadband availability. And thanks to all the speakers, they did a lot of good introduction, so I could skip a lot of the stuff. Mobile networks are important. I mean, we don't really talk about this. But what is interesting is more use cases, like public safety communications, are considering using those networks just for cost reasons, right? And this is already happening now in the UK. They start using Everything Everywhere, which is a commercial operator, from next year for providing public safety communications. So availability is quite important. And of course, we have a threat landscape with natural disasters, as we've seen recently. We have cyber attacks. We have complexity. And now we move it to more softwareized networks, so complexity is going to increase. And we have lots of interdependencies between the operators. So here, this is just a schematic showing dependencies between operators in the Norwegian market. Dependency here means that one operator is buying infrastructure, leasing infrastructure, or using base stations from another operator. So the ecosystem is quite complex. I mean, you could look at it and you could start thinking, I mean, if there is a failure, it could be wherever. I mean, it could be related to an operator that you lease fiber from and so on. And there is one operator, which is Telenor, that is sort of like the narrow waist, because they run a fiber network interconnecting the whole country. Now, so what we want to do here, we want to use end-to-end measurements to assess mobile broadband availability. Why we want to do that? Because tomorrow starts today, right? I mean, the future starts today, so we need to understand the level of availability that today's networks are able to provide before we can improve that. And once we do this empirical evaluation, we move to the next level, which is if there's any avenues for improvement. And of course, we'd like to contribute a methodology to allow us to continue doing this going forward. But this is not easy for two reasons. The first reason is that there is no single metric that describes availability. So it really depends on how you look at it. I'll come back to that. And also, as I just showed, the dependencies make the problem much more complex than one operator's problem. So you have dependencies. If you want to assess availability, you need to look at the whole ecosystem. You cannot only look at a single operator. Right, so the rest of this talk, I'll start by presenting the measurement setup and approach, and then I talk a little bit about the availability from a single operator perspective, and then I look at our effort, I talk about our effort in quantifying the impact of the shared infrastructures, and I'll talk a little bit about how we can improve availability. Right, so we have built in Norway a measurement infrastructure for measuring commercial mobile operators. That's a predecessor to Monroe, which we call Nordnet Edge. So we started building this back in 2012. It's been operational since 2013. So basically, we have a number of measurement stationary measurement nodes, about 100 of them, that are spread all over Norway. So those nodes are placed at homes, government offices, schools. So and they are basically single board computers that they connect to several operators at the same time, and we have a back end to control them. And what they do continuous measurements. So each connection on those nodes tries to stay up all the time, tries to maintain a barrier all the time. And once we have the barrier, we send data all the time to measure packet loss, delay, and so on. We have a few nodes on trains, just read more, and the study that I'm presenting, it uses data from 2014 to 2017. Right, as Anand just presented, he showed the structure of the barrier, right? I mean, how every UE needs to establish a barrier to the EPC before it can start using the mobile network services. So the schematic here just shows just a textbook description of an LTE network. And the first service that you get from the network is the barrier. So to measure availability, this was our first metric. So if you don't have a barrier, you don't have a service. So we try to maintain the barrier active all the time. So at our nodes, whenever the barrier goes down, we try to reestablish it. So we measure the connection downtime. Whenever the barrier goes down, we try to reestablish, and we measure how frequently we lose the connectivity. Once we have the barrier, we check whether we can exchange data over that barrier by sending a packet every second between our nodes and a server that we control in the internet. So we send a UDP packet every second, a very small packet, and we use that just to measure packet loss. Now, these are two metrics that we can use for measuring availability. We combine them to get a feel of the overall availability, which is basically the useful time that you have. You look at the connection time, how much of that time you could use a connection without a connection downtime, without a packet loss. All right, so this is one way to look at availability. That's okay. It's going to scare some people. Yeah, it's coming here. Okay, so this is one way to look at availability. So the other ways, for instance, you could look at delay. If you want to measure availability, you could measure availability as the percentage of time that the network could support certain delay. You could look at it from a perspective of an application. So there are different ways. We chose this because of simplicity. And you could extend this to other ways for measuring availability. So these are the networks that we measure for operators. I'm not going to go into details here, but the interesting things about these operators, the market is very dynamic, so the relationship change over time. So that gives us an opportunity to sort of appraise our methods, because once they change, then we could check if our correlations actually, or our method actually captures the underlying infrastructure. So now I move to just presenting some results on availability from a single-dimensional view. And here is a bunch of CDFs. So to the left, we have the CDF of downtime. And then we have packet disconnection downtime, packet loss, and overall availability. So these are measured in 2016 for 3 operators. And there are differences between operators. What's interesting, when we look at the overall availability, we have very high availability from those for those stationary nodes. So the blue curve, Telenor, for 90% of the connections, you can get 99.9% availability according to our metric. So that means no is about a minute and a half downtime on average per day. So of course, if you measure moving nodes, that will go down. But at least in Norway, you could achieve this very high level of availability. There are differences between operators I'll come back to. So we went back and looked at this over time. From 2014 to 2016, we just looked at the fraction of connections that achieved 3 nines of availability, and how did that grow over time. And you can see one operator here went from around 25% of our connections and up to around 80%. And this is the beauty of having a longitudinal measurements and infrastructure that you could use for monitoring this over time. So what happened over the years is LTE rollout. So back in 2014, we had a mix of LTE and 3G. Then the effect of LTE brought us here. And the difference between the operators actually boils down to LTE, not to deployment, but one of the operators is not implementing inter-RAD handover, because our nodes are always in active mode. They're always sending data. So once, by chance, if they go back to 3G, they don't get back to 4G. And then you have all score of issues with 3G that results in packet loss. So, so the general picture is availability is improving, and we're getting very high level of availability according to our metric. So now the next part is about quantifying the impact of shared infrastructure. So what we want to do, we have shared infrastructure. We want to assess their impact on availability using this diverse setup with multi-home nodes that are spread geographically. So the challenge is, first of all, we need to think about what is shared. What is shared is usually passive components, like fiber in the access network, or sometimes they share. They don't even share components, but they are at the same location. So they share power source. So there's no way that you could really identify the shared components using active probing. You could not really use traceroute or anything, or any similar tool to identify that. So then we use correlation. So we developed a method, basically using this time series of measurements. We took every time series and binned it into some smaller bins, and then converted that time series into a binary time series where we set 1 when we have a failure, and 0 when where we don't have a failure, and then we correlate them. And that correlation gives us a value. We develop a permutation test to check for the statistical significance. And then we identified all pairs of correlation that are strongly correlated. So here we don't really look at the correlation value. Like in textbooks, you could say, okay, more than 0.5 is strongly correlated, less than 0.5. Of course, that's okay for parametric test. But here, the source of correlation is actually very weak. We talk about shared fiber out in the access network. So you don't expect very high correlation values because there are score of issues, behind all outages, a part of this fiber. So, and then we get a list of, or a set of all strongly correlated pairs and uncorrelated pairs. And then we can use that for doing lots of things that I will show you. So the first test that we did was to check whether the correlations really capture the known, to us at least, the known relationship between the operators. And we found out they really capture that, and it also captures all the changes that happened during the past 3 years, which more details are in the paper. So what can we use this correlation for? We can use it to get an idea about the failures and geography. We can use it to map outages to one root cause. So if we have this diverse, huge setup, and at any time point, there are failures. So if we see failures, several nodes experiencing a failure at a certain time point, are they correlated, or are we talking about just spurious correlations? So we could use these strong correlations to establish that. So we can use it to identify places in the country where the shared infrastructure is creating a real problem. And then we can use it finally to assess the impact of shared infrastructure on the overall availability. So I'll start by showing something about geography here. So what I'm showing here, so we took all the pairs of connections that we have and we divided them into correlated and uncorrelated according to the p-value test. And what I show here is the distance between correlated pairs and uncorrelated pairs. Uncorrelated are dashed, while the correlated are solid lines. So I show here like different combinations within a single operator, between different operators. There are two lines that stand out, the solid lines between two different operators. So one between Telenor and Telia, and the other one between Telia and Network Norway. And these are a little bit shifted to the left, means that if a pair is correlated, then they are spaced by shorter geographical distance. So you could read it like about 60% of the correlated pairs are within 100 kilometers from each other. So then the cause of the correlation lies out in the access network, so they share fiber leading to the base stations. The intra operator, so correlation between connections that belong to the same operator, is no different from the uncorrelated pairs. So meaning that within a single operator, the source of correlation probably lies in the core network. So we talk about the EPC, about failures at the EPC that creates a correlation. And the same happens for packet loss. So this gives us an idea about the source of correlation. So for operators that share passive infrastructure, as expected, it lies out in the RAN, while for within the single operator, it is in the core. And of course, with NFV and SDN, we can really mitigate this, reduce the risk. Now, as I said, if there's a failure, if at any point in time we measure that, or we see that several connections are experiencing a failure, how can we determine whether this failure is actually, there's a causal link between the failures, or these failures are just randomly happening at the same time, because we have a huge setup. So what we did, at any point in time, we have, say in a given bin, we identify all connections from two different operators that experience failure and put them in two different sets. So we have operator A and operator B. And then we go to our correlation results. And we start linking, constructing a bipartite graph by linking connections that are strongly correlated. So this will sort of divide this graph into subgraphs. And those subgraphs are correlated events and outages. There are more details in the paper, and I will just show a video just demonstrating the power of this method. Let me just come back. So this is a huge area in Norway. So extending from the top north to somewhere here in Norway. So these are nodes. So each marker is a measurement node. So you can imagine these hundreds of kilometers. We're talking about hundreds of kilometers here. And each mark is a node. If it's green, that means it's multi-home. If it's green, that means both operators are operational, both connections are operational. If it's yellow, that means one of the networks is experiencing a failure. If it's red, that means both operators were down. And I will just play this. And you can see that failure starting happening. So we see yellow nodes, and now we see more red nodes. And now pretty much the whole thing is red. So this failure is fairly short. It lasted for about a minute. But it took out an area of hundreds of kilometers. And these operators are sharing infrastructure. So you see the risk in shared infrastructure. And you see the power of this correlation method, because looking at the data without these correlations, we couldn't really tell whether these failures were correlated or not. And now they are recovering. And so pretty much this is a centralized failure or a failover. We talked to operators, and they confirmed that there was a failover event. So they failed over from one fiber ring to another fiber ring. And so now everything is back. Right. So the last question is about how much these correlated failures contribute to the overall unavailability, right? So we took all the connection downtimes that we measured and removed the correlated failures to see the impact of the correlated failures. And I show here this CDF for this downtime for within a single operator and between two operators. And you could see that the correlated failures don't really contribute much to the overall downtime. So the overall downtime that wireless connections or mobile connections experience is mostly uncorrelated. It's because of the last mile of the wireless link or things that are within, the wireless link. But from the previous slide, we should remember that, although most failures are not correlated, the impact of correlated failures or the impact of shared infrastructure can be really tremendous, and it can really affect huge areas. So this is good, and there's an opportunity in this, right? Because we could use this for improving availability by combining, by multi-homing to multiple operators, since most failures are uncorrelated. And we try to assess this by measuring the overall availability when we combine more than one operator. So we took pairs of connections that are to different operators and treated them as one connection, and then we measured the overall availability when combining them. So to the left is our old plot, which shows the overall availability for individual operators, and here when we combine them. And once we start combining them, then you can get availability numbers like 5 nines. And now the question is you need to get the protocols, you need to get the methods for doing that, and so on. And you see the benefit is more for operators that don't share much. The blue line is like 2 operators that share even the base stations. Sometimes they share the base stations. This is why the benefit is not as much. Right, so this benefit of multi-homing is also extends to moving nodes. So we also assess the effect of multi-homing or the benefit from multi-homing when nodes are moving, and with that on trains. And we could see that also on trains as you're moving. And of course, trains are really difficult because they are iron boxes, right? So they attenuate signal and so on. So even on trains, we could get up to 3 nines of availability, except for the second node here, because that line is really poorly covered. So just to conclude, we see that the availability is increasing. Of course, at least for the stationary nodes, but still inconsistent. If you look at the CDFs, and remember from the CDFs, we see variations across nodes, and it's at most 3 nines. Correlated failures don't contribute much to the overall unavailability, but when they happen, they can potentially affect a large number of nodes, a large number of users. And of course, this varies from a country to another. It depends on the markets in different countries. And of course, we need to rethink sharing, and probably the potential for solving sharing problems, with more softwareized networks. And multi-connectivity can help at least use cases like public safety communication or military, which would like to have higher level of availability. Thank you.